Having made a preliminary study of data structure design, we shall now go back and study some aspects of the design of algorithms and try to make out how to what are the basic steps which are involved in algorithm design aspects which are not purely data structure design concepts. We will just revisit some examples which we did before, and we will see some of the very important issues which are related to the design of algorithms and related to problem decomposition and how to generate a good algorithm from an initial problem or from an initial solution. We have seen before that we will use recursive definitions to define a problem, and now we will see how, given a recursive definition, how we could analyze it further to obtain an algorithm which does not have some of the defects of the original recursive algorithm. And later on, this algorithm design and data structuring will go hand in hand to make a complete design of an algorithm, or to constitute a complete design of a solution. So we will have a quick look at these aspects of algorithm design, because this is these two aspects will be integrated for program development. Among the three, we will study three major concepts. That there are three major aspects. One of them we could term we have seen this idea before, balancing the split, when we did finding out the minimum of n numbers or sorting of n numbers, and we discussed the issue of where to split the list into two parts and how it leads to recurrence equations which are to be solved to find out the optimal split. So this is one aspect. The second aspect, this is usually called balancing in classical algorithm design terminology. The second is identifying identical subproblems. You will see that when you give a recursive solution, several subproblems will come which are identical, and you would like to solve them only once rather than solve them again and again. And the technique for identifying identical subproblems and solving them only once has got a name which you will see in textbooks. That name is called dynamic programming. It has a different meaning or a different style in other aspects where you come to state machines, and there you talk of dynamic programming in a slightly different sense, but inherently both of them have got very, very similar meanings. And third, which we call pruning, where you try to see which of you can make a choice between subproblems and choose only one of them, or decide that this subproblem need not be solved to solve the original problem. And here you read two types of strategies you will see. One is called the greedy approach, the other is called the branch and bound. So we will see what these things mean and try and get a flavor of how algorithm design involves these three core aspects. There is no formal methodology for this, but these are some intuitive ideas which can be formalized by trying out various solutions and solving them. We will get a very good idea of what it means. I would not like to go into an actual formal definition of all this, because that would lead to more terminology only. So the first aspect we will take is balancing, because we have seen this before. And to quickly recapitulate, in balancing we were given a problem and where we had split the problem into two or more parts. And in the solution, we did not choose where to split in the initial solution. We will only analyze and then say where to choose. Let us see some examples. Suppose you have to find the maximum of n numbers. Now to find the maximum of n numbers, given a list L, what was our recursive solution? If the size of L was 1, then obviously the problem is the base condition. Otherwise you split into two non-empty sets L1 and L2. Alright, and then solve these two recursively, and after you solve these two recursively you get M1 and M2, M1 from L1 and M2 from L2, and then you compare these two and get the final solution. So where will we split? Will we split in the middle? Will we split left? Will we split right? So to answer that question, we saw that you have to solve recurrence equations. For example, here the recurrence equation is related to the number of comparisons that have to be made, because here the number of comparisons for n numbers is equal to 0 when n is equal to 1, and is equal to the number of comparisons in the first split list plus the number of comparisons in the second split list plus 1 when n is greater than 1. Alright, so this was how we solved the problem, and if you open up this, you will see that this will come to, you replace Ti, Tk is equal to k minus 1, and you will see that the recurrence is solved. Tk is equal to k minus 1. The solution to this, whatever be n1 and n2, will be k minus 1, because you replace this, this will be n minus 1, n1 minus 1, this will be n2 minus 1 plus 1, this will come to n1 plus n2 minus 1, and we know n1 plus n2 is equal to n, because you have split n into n1 and n2, so n1, so this will be n minus 1. So what does this reveal to us? This reveals to us that whichever way we split, whatever are the values of n1 and n2, you are going to require n minus 1 comparisons. So you can split it in any way you like, and the algorithm will be correct. So the choice is now clear. You can choose anything you want. You split 1 n minus 1, 2 n minus 2, or whatever, and therefore the problem can be easily solved, and it will be optimally solved. All of them are optimal. So now we are left, suppose we make a choice and we make 1 n minus 1. Now the next step is what have we chosen for representing L. So we have balanced the problem optimally and we have chosen 1 n minus 1. So now we are left to choose the data structure for L. Till now L is a set. So what are the operations on L now? If it is 1 n minus 1, it is remove the front of the list, so head and the rest of the list. So if you remove the front of the list, you will get two parts. So now suppose you are given L and you read in the elements, first you read in the number of elements, and then, so you can use an array to solve this problem without any difficulty, or even if you use a linked list to solve the problem also, there is no problem, there is no difficulty. So using an array or a linked list for this set L and choosing the first and the rest, the problem can be solved optimally. So this is, I am using a very simple problem. I have shown you how you split the problem, how you have chosen the data structures for L, and that's all. You can now finalize your complete code. Alright, any questions? Let's take another problem, sorting. And here in the merge sort style, we saw that when L is equal to 1, the problem is solved. Otherwise, again you split into L1 and L2, which are non-empty. You recursively solve these two to get L1 dashed and L2 dashed, and then you merge these two by a merge algorithm. and we saw that the recurrence equation which crops up in this situation is Tn is equal to Tn1 plus Tn2 plus some Kn, because the merge algorithm is linear time. We know that merge algorithm can be done in n comparisons when there are n elements. So you can choose any constant into n, this is what it will take, and T1 is equal to 0. And we saw that if you take n1 equal to 1 and n2 is equal to n minus 1, then this will lead to order n square. On the other hand, if you take n1 is equal to n by 2 and n2 is equal to n by 2, you will get order n log n. So you have decided to split in the middle. Now once you decide to split in the middle, the choice of split is now made, so we are left to design the data structure for L. Now if you choose a linked list to make a data structure for L, splitting will again be expensive because you will start from the beginning and split. You will have to scan from the beginning and find out the middle element. On the other hand, if you could work it out on an array, and if you knew the ith and the jth, the start and the end index, then the middle element can be simply chosen by this computation. So if you could know the dimensions, the maximum limits on the array, then obviously it is best to use an array. On the other hand, even if you don't know, after you have read all the elements, you just put them into an array, malloc an array of that size, you know these are the elements, you malloc an array of that size and work on an array. That will be fastest because this split, otherwise even for splitting you will take linear time. That will not affect the complexity. Overall order n log n will remain because it will only add some more constants to this part. Splitting will take some k1n and merging will take k2n, and they will add up to form some k3n. So you will get T n by 2 plus n by 2 plus some k3n, which will still be order n log n, but with an array the access and the split will be at least constant time. But n log n is ensured even if you use a linked list. Is that understood? So this is how you proceed to do a data structure design subsequent to the design of the algorithm. Now let us choose another problem which we have done in a slightly different way. Max and min, the maximum and the minimum of n numbers. Similar, we will use a similar approach. If L is equal to 1, size of L is equal to 1, then the recursively max and min returns two values, isn't it? It will return the maximum and minimum, so it returns a structure. So if L is 1, it returns AA, that is, which is if L, because L was equal to A in this case, only one element. If L is equal to 2, then it returns a comparison of, and suppose L was AB, then it compares A greater than B. If A is greater than B, then it returns BA, AB, else it returns BA. Alright. Now two elements. When you come to more than two elements, you split into L1 and L2, okay, and recursively you will get max 1, min 1 from solving L1. Alright. You recursively solve max and min L1, that is, you will write max and min L1 to get max 1 min 1. You recursively solve max and min N2 L2 to get this. Now you compare max 1 and max 2 to get max. Max is equal to compare max 1 and max 2, and min is equal to compare min 1 and min 2, isn't it? Suppose this base condition is clear. When L is of size 2, you make one comparison and you will get the maximum and minimum. When L is more than 2, then you split into L1 and L2 and recursively solve L1. L1 will return some max 1 min 1, L2 will return max 2 min 2. The maximum of L will be the larger of max 1 and max 2, and the minimum of L will be the smaller of min 1 and min 2. Alright? Any questions? So this is one approach to solve the problem. So let us see what recurrence relation this gives us. This gives us Tn is equal to 0 if n is equal to 1, is equal to 1 if n is equal to 2, and is equal to T of n1 plus T of n2 plus 2 for n greater than 2. Alright. Now where will you split this up? Where will you split this up? If you choose n1 equal to 1 and n2 is equal to n minus 1, then can you guess what this will lead to? This will lead to order okay, work it out. 1 plus T of n minus 1 plus 2, sorry, 0, 0, 0. That will lead to 0 plus 0 plus T of n minus 2 plus 2 plus 2 . To n minus 1, isn't it? Order n, but 2n minus 1. Now suppose you split in the middle, and let us take for example that there are only 2 to the power n elements, okay, and you split in the middle, then what would you get? Tn is equal to T n by 2 plus T n by 2 plus 2, right? So suppose this is of some 2 to the power k, it will make it easier to analyze. So T of 2 to the power k is equal to twice T of 2 to the power k minus 1 plus 2. We have chosen 2 to the power k equal to n. That is, suppose n is 16, then 2 to the power 4. So this will, can you solve this? This is 2 into 2 T to the power 2k minus 2 plus 2 plus 2, right? So that is equal to 2 square T to the power 2 to the power k minus 2 plus 2 square plus 2, 2 to the power I T 2 to the power k minus I, right, plus 2 to the power I will this term come? Try another term from here and see if this term comes. 2 square and open up 2 T to the power k minus 3 plus 2 plus 2 square plus 2. So you will get 2 cube k minus 3 plus 2 cube plus 2 square plus 2, right, if you open up. So what does this lead to? This 2 to the power 0, we will make it up to 0. When this will become 0? When I is k. So 2 to the power k, then t1 plus what? Have I made a mistake somewhere? 1 minute. If this sums up, it will come 2 to the power k plus 1 minus 1, isn't it? I think I have made a mistake somewhere. No, t1 is equal to 0, you can cut it out. That's all right. But this equation was tn1 plus tn2, that's fine. I think I have made a mistake somewhere. Huh? This is 2 to the power k minus 1, n by 2 is correct, plus 2. It's okay, na? So this comes to twice n minus 1. This is not the correct solution somehow. No. This is not the correct solution. Let us work it out for 8 and see how many comparisons come. Let us work it out for n equal to 8. For 8, you split it into 4 and 4. No. I have understood where I made the mistake. 2, 2, 2, 2, right? You will not go beyond 2 because your recurrence stops at 2. So we have actually stopped it at 1, but we should have stopped it at 2. Got it? So this part is correct, this whole thing is correct, but it would have stopped at T2. It need not have gone till T1. So let us proceed from there. So we were at 2i t 2 to the power k minus I. This is correct. The expansion is correct. But what the mistake we did was we broke the recurrence, we made it from 2 to the power 0. That is 1. But the recurrence will stop at 2. So I will be k minus 1. So we will stop at 2 to the power k minus 1 t2 plus this will be 2 to the power k minus 1, right? Is that understood now? That is the advantage of that T2 because here we stopped at 2, not 1. And this would give us, how much is this? N by 2 into T2 is what? 1 plus N minus 1. So this gives me 3 by 2n minus 1. So now see, while both for order n, splitting in the middle gave me slight reduction in the number of comparisons. So I would still split in the middle. But is this the only option? Let us see. If you analyze it a bit more carefully, you will see that in any tree developed like this, see this will split up into things like this. Given say n, it will split up into two parts, n1 and n2. Say n3, n4 like this. The leaf nodes will be of two types. If the n value here, that is the number of elements, is 1 or 2, and the internal nodes will have more than 1 or 2. Clear? Internal nodes will have more than 1 or 2. Now internal nodes are those nodes where the split occurs, and the number of comparison at every internal node is 2. The number of comparisons at every internal node is 2. At the leaf nodes, it is 0 for this and 1 for this. Okay. So to solve the problem optimally, what would you do? Suppose you had got 4. The choice here is 4 can be split as 2, 2, and 4 can be split as 3, 1. And then 3 has to be split as 2, 1. Now whenever you split it into 2, here this is optimal compared to this, just have a look. Now let us see 6. I am not going formally purposely, just to 6 could be split as 3, 3. This is not 2 to the power n. 1, 2, 1, 2. What is the cost? 0, 1, 0, 1, 2, 2, 2. What is the total cost? 8. And if I split it up as what is the total cost? 7. So even splitting in the middle is not optimal. To get an optimal split, you have to analyze the tree. If you minimize the number of internal nodes, you have some external nodes. Now all internal nodes are of maximum cost. The external nodes cannot be both 1, 1 unless the internal node is 2. So if you minimize the number of internal nodes, you will get the maximum benefit. I repeat, every internal node is of cost 2. Alright. Now if you minimize the number of internal nodes, if there are 2 internal nodes, there will have to be only 3. If there are 2 internal nodes, then how many external nodes can there be in a tree? If for 2 internal nodes, can there be 4? For 1 internal node, there can be 2. So let us take the base condition. For 1 internal node, there will be 2 leaf nodes maximum. Now if there are n internal nodes and there are n plus 1 leaf nodes, then if you make 1 internal node, for every internal node if you make 2 more leaf nodes, then you will gain, this will increase by 1 and this will increase by 2, because 1 internal node has now reduced and become 1 leaf node has become an internal node. So suppose see, take this case, there is 1 internal node and 2 leaf nodes. Okay. Now if you increase the number of leaf nodes, you will choose one of them. So 1 leaf node will vanish and 2 leaf nodes will get added. So effectively 1 leaf node will get added, isn't it? So you can show that for n internal nodes, there will be n plus 1 leaf nodes maximum in this structure. And though I do not wish to go into more details, you can just analyze it a little and see that if you minimize the number of internal nodes here, then you will get the optimal split. Not even half does not optimally split it. That worked because we chose 2 to the power of k, and in 2 to the power of k everything will land up in 2's at the end. So the choice, a better choice would be, if n is even, split even. If n is odd, split odd even. If n is odd, one internal node of cost 1 has to be there. Okay. So if you choose a split this way, that if n is even, split even, if n is odd, split odd even, you will get the optimal solution. You can work it out in your rooms and check. It is even better than half because half will not split it that way. So one choice is take out 2 at a time. Suppose you have got 6. Take 2 at a time out. Suppose you have 9. Take 2 at a time out. 2, 7, 2, 5, 2, 3, 2, 1. It will be optimal because you have split. If it is odd, split odd even, it will work. And if you split it this way, you will always get the optimal solution. So once you decide on your split, so this is one problem which you can decide on your split and you will get the optimal solution in terms of number of comparisons. And one such split is just take out 2, 2, 2, 2, 2, 2, 2, 2. And now once you have decided this, your data structure design is left. So now you can use it as an array or a linked list, it will not matter, because you have to take out 2 elements at a time. So in constant time you can split the list. On the other hand, if you split in the middle using a linked list, you would have had problems. Suppose you chose middle, you cannot split in the middle using a linked list. You would not get a constant time split. So if you split in the middle, you have to use an array. On the other hand, if you split like this, you can use a linked list or an array. So this way you can balance the split. Balancing has got some other, there are several interesting problems related to balancing, and you can see in the book 1 or 2 of them. One is multiplication of 2 n-bit numbers. Normally we could multiply 2 n-bit numbers in order n square time, assuming that addition of 2 bits is constant time, and addition of 2 bits, if addition of 1 bit and 1 bit is constant time, then addition of n bits and n bits is order n time. Alright, then you can do multiplication in order n square time. You have a look at the book, any book on this one, especially Aho, Upcroft, Ullman or Codman, you will see that if you split it up in a very interesting way, you will get order of n to the power 1.59. How 1.59 comes is an interesting feature. It is related to how to balance this split. Secondly, in a very similar vein, multiplication of 2 n by n matrices. Normally we could do it in how much time? How many individual multiplications would you require and additions? N square or n cube, isn't it? N cube. N cube. Our standard loop algorithm will take n cube multiplications. Every row with every column. So to produce every element here, we require n square order n comparison multiplications. In C is equal to A into B. So for every element in C, we need to make n additions and multiplications, isn't it? A11 into B11, A12 into B21, A13 into B31 that way. So to produce every element we require n such operations. So to produce n square elements we will require n cube operations. Now if you split the problem and multiply it 4 by 4, split it into 1/4 size. Okay, so you split A into A11, A12 into 4 parts, into 4 submatrices, and similarly B. And then do a recursive multiplication of them in a very intelligent way, then you will be able to reduce this to something order of n to the power 2.83. These come from log values. Okay. So this algorithm is called the Strassen's algorithm. You must have heard of the name before maybe, but so these are all related to how to optimally balance the split. So this is one aspect of algorithm design. Next day we will have a look at dynamic programming.